Hello, welcome to another lesson in Algebra 1. Today we're covering section 1.7, representing functions as graphs. So we've already seen functions represented as tables, as mapping diagrams, and as a rule. Okay, so we're adding graph to this today. All right, so as always for the warm-up, if you haven't tried it yourself first, please pause the video, do the warm-up yourself, and then come back and check it over. All right, number one, complete the function table that matches this function mapping. So all the questions are about this mapping. This is our input, this is our output. You can tell because of the way the arrows point. And our first input points to 8, and that's already represented in the table. The second input is 2, and that points to 16. The third one is 3, and that points to 24. And the last one is 4, and it points to 32. Okay, so we're supposed to write a rule for this function. And our rule here is times by 8. We take each of the inputs, and if we times them by 8, we get the outputs. So that means we take our input variable, our independent variable. If we times that by 8, we'll get our dependent variable. Remember, we can't find our dependent variable because it depends upon what we pick for our input or our independent variable. Okay? Number 3, what is the domain of this function? So the domain was the set of all of the inputs. And the inputs were 1, 2, 3, and 4. Okay? Number 4 says, what is the range of this function? The range is the set of all of the outputs, and that is 8, 16, 24, and 32. All right, lastly, if you change the input 1 to a 2 in either the table or mapping, why will this no longer be a function? So in here, if I make it a 2, then the 2 would point to both 8 and 16. We would only put 1, 2 in our mapping. And in this guy, let's see. If I make this a 2, then you can see the 2 points to 8 and the 2 points to 16. Okay? So this violates our third part of the definition of a function. It still has a list of inputs, it still has a list of outputs, but there's no one-to-one mapping between an input and an output. We have one input that makes 2 different outputs. So now I would say something like this. Input 2 maps to 2 different outputs. And that's not allowed. Okay? All right, so our new stuff for today. Number 1, the table shows the number of pets in a home P as a function of the number of children C in the family. So P is our output, or in this case, it's going to be our dependent variable. Okay? And C is our inputs or our independent variable. Okay? It's always written that way. The dependent variable is a function of the independent variable, or the outputs are a function of the inputs, is a way to think about it. All right, so here's our table. So these are our inputs, or the domain, and these are our outputs, or the range. And we want to make a graph for this. All right, so our graph is set up with our scales. With our axis, but it does not have a scale on it. So we need to put our scale. So 0, 1, 2, 3, 4, 5. We go by 1, so this would be 6. And 0, 1, 2, 3, 4, 5, and this would also be 6. Okay? So then I can plot my points. First point is 0 children makes 3 pets. That's right there. The second point is 1 child. That family has 1 pet. The third one is 2 children. That family has 3 pets. And the fourth one is 3 children, and that family has 5 pets. Okay? So this would be the graph. Our domain had only 4 points, so our range has only 4 points in it, or 4 numbers in it, values in it, and that means we end up with just 4 total points here. Now, if we were to ask more than 4 families, we probably would no longer have a function, because I bet we'd find a family that had 1 child and maybe 2 pets, or 0 pets, and then we'd have more points on this line right here, along with every other one. Okay? But right now, since we only asked 4 families, we ended up with 4 points, so it ends up being a function. All right, write a function rule for the function represented by the graph. identify the domain and the range of the graph. So we have to write a function rule. We have to find the domain and the range. Okay. So here's our graph. We have these points. And first thing we're going to do is we're going to make a table so we can help see what the ordered pairs are better. So the input 1 made an output 5. That's this guy right there. Then the input 2 makes the output 7. And so forth. 3 makes 9, and 4 made 11. And we didn't need that last spot there. All right, so here we go. We're going to find a pattern between the input and output values, or relationship. Okay, so we're going to write a rule that describes that relationship. Okay, all right, so let's see, what would our rule be? Well, this rule is a bit trickier here. In this case, we are doing two things. We are not just multiplying by something, like we could try 1 times 5, but 2 times 5 would make 10 there. And we're not just adding. We could try 1 plus 4 for 5, but 2 plus 4 would make 6. We're actually doing a combination of both of these. So what we're going to have to do is multiply by 2 and then add on 3. Okay? Here's a trick for how I know that. You can see that the change between each x is 1, and the change between each y is 2. So if I take the change in the y's, or the outputs, and divide it by the change in the x's, I get what will be the multiply part. This is what we need to multiply it by. This is a linear function, and you can tell because this graph, if I was to connect them all, would make a line. And if it does all make a line, then we know that we could use this rule of the changes between the outputs and the inputs, divide it, and we'll find out what it's multiplied by. Okay? All right, so the rule for our function here is 2x plus 3. And the domain of the function is 1, 2, 3, and 4. And the range is 5, 7, 9, and 11. Okay. All right, our last page. Graph the function y equals 1/2 x plus 3. So we have our function rule, we have a domain, we want to make the graph. So I put my input variable, my output variable, the domain corresponds with the input variable, and then I plug those into my rule to get the output variable. So we'll do them in black here. I put 0 in for x, so 1/2 of 0 is 0, plus 3 is still 3. And then I plug a 2 in for x. Half of 2 is 1. 1 plus 3 is 4. I can plug a 4 in for x and so forth. Half of 4 is 2, plus 3 more is 5. And then 3 plus 3 for 6, and 4 plus 3 for 7. Okay? All right, so now I need to plot these. So 0 through 3, or 0 through 8 on the x-axis. So we'll just go by 1s here, I think. That's 1, 2, 3, 4, 5. 1, 2, 3, 4, and that'll make 10. And we can go by 1s on the y-axis also. 1, 2, 3, 4, 5. 1, 2, 3, 4, and then that would be 10. Okay, so I'll plot each one of these points. 0 makes 3. 1, 2, 3. 2 makes 4. 2 up. 2 over 4 up. 4 makes 5, 4 over 5 up. 6 makes 6, so 6 over 6 up. And 8 makes 7, 8 over and 7 up. Okay? All right, it didn't ask us, but our range, remember, is this list, 3, 4, 5, 6, and 7. All right, number 4, graph the function y equals negative 2x plus 7 for this domain, negative 1, 0, 1, 2, and 3. So we'll make a table again. Negative 1, 0, 1, 2, and 3. And let's see. Plug negative 1 in will give us negative 2 times negative 1 plus 7. So that's 2 plus 7 for 9. If we plug 0 in, we'll get 7. If we plug 1 in, we get 5, and then it keeps going down by 2s, 3 and 1. Okay? All right, so we have a little problem with graphing this one. I'm going to choose to fix that by going over a little more. So this is going to be negative 1, 0, 1, 2, 3. Okay, and then 4, 5, 6, 7, 8, 9, 10. And then on the up way, it's going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. Our first point is at -1, +9. Our second point is at 0, 7. And then 1, 5, 2, 3, and 3, 1. Okay. So this would be our ordered pairs all in blue here. That represents this rule over that domain. Okay? All right, so this concludes our notes for today. I will see you in class next time as we extended and learned a little bit more about rules for linear functions.